Okay, so we left off with sunspots. So the question is, what are sunspots? Are they super hot? Are they super cold? What causes them to be there?
Is it like just a land? Little mini island?
Nope. That might be a good guess, though. And actually, if you had to pick a spot on the sun to hang out, these would be the best little islands to be on, for reasons that you'll see soon here. These sunspots are caused by the sun's magnetic field. And the way it works is this. The sun has a super strong magnetic field. And those magnetic field lines come up from underneath the sun, and then they go back down in certain locations. And those locations are the sunspots. So they take a few days to over a month to form. You don't need to write any of this down. But in order to figure out exactly why these sunspots are there, we're going to get to that in just a second. In order to build that up, though, we have to make sure that we know why these spots are actually cold. Go ahead and skip this slide.
Yeah.
So, you guys have seen magnetic field lines before, right? Some science class. This is like a little horseshoe magnet. You'd see the magnetic field lines coming around from one end to the other. And the same thing is true on the sun. Its magnetic field lines go through, and then they come back in. So the sun is made up of really, really hot plasma. And because that plasma is ionized, that means they're affected by the magnetic field of the sun. So they're kind of getting trapped in these magnetic field lines, which is why you actually can see those lines so clearly there. And they don't like stick in one spot, they actually spin around each of those lines. And what ends up happening with these sunspots is, we talked about the convective layer of the sun yesterday. Again, what the convective layer does is everything's super hot underneath the sun's surface, and all that hot stuff rises, just like warm air rises on Earth. The further away it gets, the more it cools down, and eventually you get to a point where it's cool enough that it goes back down. And then it gets hot because it's getting closer to the middle, and then it heats up again, and it just cycles through that way. So what ends up happening is these spots where you've got the magnetic field lines coming through, they're interrupting this convection cycle. And they're not allowing any of the new hot material to make it up to this location. So it's like this is a cold region that's not allowed to descend. And so these dark spots are indicative of places on the sun that are really, really, comparatively speaking, cold. 4,500 degrees Kelvin is still really, really hot. You'd fry to a crisp instantaneously, but it sure beats, several million degrees. So yeah, these are cool spots on the sun there. Yeah. So these are the locations you'd want to go to if you wanted to last as long as possible on the surface of the sun. And the interesting thing about the sun's magnetic field lines is that they switch, and they switch relatively often. What ends up happening is, because the sun is so massive, and because it's so big, and because it's a big ball of gas, the equator spins much faster than the poles. And so if the equator is spinning much faster than the poles, it drags those magnetic field lines along with it. Because again, the sun is made up of plasma, those ionized particles. So they interact with that magnetic field, and in this case, they actually drag it along. And they make it all messed up. And eventually, over about 11 years or so, you get to a point where they're just bent totally out of proportion. And eventually they get so bent up that the entire magnetic field switches from north to south, and you start all over again. So it goes through an 11-year cycle like that. This is what it looks like when it's most active, when those magnetic field lines are getting all bent out of shape. And then when it flips and it gets all peaceful again, this is the sort of thing it would look like. So big, big difference there. And you can see on this graph here, sunspots change over time based on that cycle.
Is that your graph?
In all honesty, it does have my name on it, but this is not from me. So there's some other astronomer out there named Hathaway who is probably also good looking as well. So the other thing we want to talk about, oh, I don't even have the fan on. That's risky. There we go. Now it's on. So this would say solar prominence there. You want to write down solar prominence in your notes. Solar prominence. And this down here is an example of a solar prominence. We'll get to what those are right now. From this slide, go ahead and write down the first bullet point. Yep, the first one. And the picture on the right is a prominence. You've got these particles that are trapped inside the magnetic field of the sun there, and that's what you're seeing. You're seeing that super hot ionized plasma being trapped in those lines. Yes, Clint?
How do you get qualified? Like, how do you know when something is a star? Like, when something qualifies as a star?
Basically, you have to have the nuclear reactions occurring in the core. If you don't have those, you're not really going to be giving off light. So it has to be big enough and pressurized enough that that fusion is occurring in the middle. Good question. So what ends up happening with these prominences then is once the magnetic field moves, they just rain back down to the surface because they're no longer trapped inside those lines. So this is an example of a prominence right here. This is a real one taken from a camera that must be pretty close to the sun there. And it looks, very menacing, but once the magnetic field moves, all of this stuff is just going to rain back down on the sun. It's not going to blast out to space and hit us. That's something we'll talk about next, and those are called solar flares.
Would it get hotter? Like, because it's technically closer to us, would that be hotter?
Well, the distance it travels from the sun to us is great enough that it would cool down. So we won't feel it as a temperature change, but we would notice it as radiation. So it's kind of interesting what happens when all that radiation hits the Earth. Another example of a prominence is right up here. And just to give you an idea, remember the Earth is much smaller than the sun. So there's the size of the Earth compared with a standard prominence on the sun.
So even the prominence.
Yeah, much bigger. Thankfully, we're not close enough that those are going to affect us. Now, when the sun does get angry, and it does start to spew its material out into space, it does something called a solar flare. And that's what's coming next here. Write down solar flare. So solar flares occur primarily for the same reason that prominences occur, but they're kind of like prominences on steroids. And you can see exactly why that is when you consider what happens to a magnetic field as it gets more messed up. From this slide, just write down that it occurs due to a magnetic reconnection event. It occurs due to a magnetic reconnection event. Magnetic reconnection event.
Magnetic, that's it.
Yep. Solar flares are caused by those. And I'll just kind of walk you through what happens in that.
Can you see that happening now? Can you see that happening now?
No, not without a special telescope. We can feel the effects of it. They certainly felt the effects of it in 1859 when a huge one occurred. You'll see some of those things coming later here.
Wait, do they have like, with like the Hubble Space Telescope or, can they like dim it so like you can look at the sun without blinding or something?
Yeah, I mean, they can't point the Hubble at it, but other Earth-based telescopes they do. Yep.
So is there like a way
Yeah.
to like, yeah.
Basically, yeah, you put a huge filter on it that cuts the light down. And another thing people do is they point telescopes at it, and instead of actually looking through the eyepiece, they put a piece of paper up next to it, and they can see like sunspots and things. And you can probably guess, these solar flares are a lot more likely when you have a lot of sunspots, because you've got a lot of sunspots when all those magnetic fields are going through a lot of distortion. And that's what ends up causing prominences and solar flares. What occurs with a solar flare is, imagine you've got this like little prominence thing happening here. You got the magnetic field lines coming out and going in. As those magnetic field lines grow and get more and more distorted, they get bigger and bigger and bigger. And eventually you get to a point, you see this right here? These magnetic field lines are getting very, very close to touching. Once they touch, they reconnect on the bottom, and the magnetic field basically gets neutralized down there. When it's neutralized on the bottom, there is nothing holding this top part of the magnetic field down. So it used to be where, this is all just being held together as one thing. But if you take out the portion that's holding it down, the top part can just lift up and go out into space. And that's what's occurring right here. These magnetic field lines connect, and when they connect, it's like you just kind of cut it off in the middle. And when you do that, there's only one force acting on this cut-off magnetic field, and that's an outward force. And it goes out into space in a random direction. And if it hits Earth, things tend to happen. And you'll see what those things are in a little bit. You can kind of think of it like kinking up a garden hose too far. You can only twist it so much until you get it breaking and you get water leaking out. That's essentially what's happening to these magnetic field lines. They can only twist and turn around each other so much before something has to give. And that's what happens when a solar flare occurs. Solar flare right there. Another one's occurring there, and you can tell they look much more violent than prominences. This next one is a pretty well-known one. You might have seen this one somewhere before. This is one that's actually you can see in video. And maybe we'll look at this when I turn the camera off.
How do we take a picture?
We've got satellites that are relatively close to the sun, and they're equipped with telescopes and filters that we can look real close at it. This isn't like, it's not really this close, It's zooming in from a long ways out, yeah. All right. Write down the most powerful solar flare occurred in 1859. No, just most powerful solar flare, 1859.
Have you seen the movie Vancouver?
No.
That's, well, in the second one, or actually in the real world, it's like a apocalyptic world, and it's because like there was a bunch of solar flares. So like they say the Earth is scorched.
Sure.
It's like really like it's super hot and like everything's like that.
Interesting. Yeah, solar flares would not heat up the Earth, but it would cause a lot of radiation damage.
Did you watch that movie? Like, it's not like four or something like they traveled to the core.
Oh yeah, I did see that.
Yeah.
Yeah, that was an interesting movie. I think that came out when I was actually working at the movie theater, way back in my high school or college days. But yeah, so for this, they actually knew that it was coming because the bigger a sunspot is, the more powerful the solar flare is going to be. And they noticed a sunspot that was larger than anything they had ever seen before. These are big sunspots right here, very large. And they saw one that traveled from location A here to B, wheeled around to C and D. And you can see the result of its path in this area here. So they knew that this solar flare was very powerful, and it did end up hitting the Earth. So also write down that it was the largest geomagnetic storm in history. Geomagnetic storm is the result of a solar flare hitting the Earth, or other particles from the sun encountering our atmosphere. And I'll tell you what, we just got pelted by this storm. And you can kind of see a little representation here. The sun, what's that?
So you felt that?
We felt the effects of it, yeah. And you'll see how shortly. The sun blasted that radiation out to the Earth. Thankfully, we have a magnetic field that deflected it for the most part around us. If we didn't have that magnetic field here, we wouldn't be here today because of that. So all that radiation did find its way around the Earth, but some of it did make it through because there was just so much of it there. The magnetic field can only handle so much. So what ended up happening then is you got these effects. I'll just give you some time to read these.
Yeah. So basically,
Yeah, so this was pretty crazy. So aurora we're seeing all over the world because aurora occur because you're getting these ionized particles from the sun that find their way to the north and south poles because that's where our magnetic field lines separate. So they just kind of funnel them in up there. And if you get enough, you can see these aurora, a ways further south. You usually can't see them here. I've seen them once or twice in my life, but it's a very rare thing. So they were seen all the way over the world, even in the Caribbean, like near the equator there. And these aurora, the northern lights, were so bright that people actually started waking up in the Rocky Mountains region and started preparing breakfast because they thought it was daytime. It was that bright. That's how powerful these aurora were. You could actually read newspaper. Telegraphs failed and shocked their operators because of all that radiation, messing up all the electrical equipment. And telegraph pylons threw sparks everywhere. So, if you're talking about something that could really just mess up our world, aside from a global pandemic, imagine what would happen if something like this happened right now. Like, in 1859, we weren't exactly dependent on satellites and electronics. And when we were using telegraphs and things like that. So yeah, you shock your operators or whatever. and you get some sparks there, but that was the end of it. We are so dependent on electronics, on satellites, on, the World Wide Web, that if that would go down and this thing would fry the electronics on the surface of the Earth, I can't even imagine what would happen. So this is the sort of thing that I don't think gets enough attention in terms of preparation. We need to be ready in case everything goes down. If the internet goes down for a week, that's the sort of thing we need to be ready for. So yeah, we'll see what happens, but we'll get a good couple minutes notice before it would hit. But so yeah, you can see this is on a high note. We'd be able to see awesome northern lights again if that occurred.
So would all the power be out? Like any electronic would be
Gosh,
fried?
something that strong, unless you've got like an emergency generator that's not hooked up to some direct power source like that, yeah, the power would be out. You'd need battery-powered things that don't operate with ports. So, does solar activity affect us? This is a big question. So, let's see. This graph shows sunspots and how they were recorded from the 1600s up until about the year 2000. And in this area, from about 1650 to the kind of first quarter of the 1700s, very few sunspots were observed for some reason. Nobody really knows why. But when they were looking at the sun through their telescopes, and again, not with their eyes, but they'd hold up a piece of paper to the eyepiece and they could see the sunspots, there just were no record of any for that period of time for some reason. And it's sort of interesting that this period of time coincides with something known as the Little Ice Age from 1645 to 1715. It's a pretty big coincidence that that would happen and not be related to this sunspot activity. So, and also, just going back, 3 other cold periods occurred during periods of small solar activity. This period right here, and not quite sure exactly what the other one is. Maybe it's in this area. But we saw noticeable cooling on our climate based on those sunspots being absent. And this is a little graph that shows average sea surface temperature and sunspots, and it kind of compares them over time. And you can see that there's a pretty strong correlation there on our overall ocean temperatures and the amount of sunspots that we find on the sun. Not that it's particularly the sunspots that are causing this change to occur, but you got to think about what's happening. What are sunspots an indication of? They're an indication of magnetic activity on the sun, which shoots out a lot of radiation, and that radiation impacting our magnetic field in our atmosphere is probably what's causing this correlation. As far as this goes, write down both of these bullet points. This is the same graph. It's it's no surprise that the sun should affect our climate. I mean, after all, it's what provides us with all of our heat. So as sunspots come and go, our temperature changes come and go too. And this kind of, I'll show one more graph, and then we'll get into what this all means. So this is just a graph of land air temperature, and that's compared with sunspot cycle. And so once again, you can see a pretty strong correlation there. And you can kind of see where this is heading. Anybody want to share any opinions or feel real strongly about the Earth, whether it's getting warmer and whether or not that's man-made? Anybody want to care to comment on any of that? You did that in Spanish today?
No, well, so we have a debate Friday. And it's like we were kind of like a side.
Sure.
Like it's between global climate change and whether you think it's natural or like man-made.
Right. Well, that's it's an opinion thing. And, as much as, well, I want to say that. So here's the thing. We hear about global warming all the time from Time Magazine and other places. And it's this huge deal. There's a lot of money in it. And the real question is it the sort of thing that we can observably prove or disprove with science? And, the thing that we have to keep in mind when we're dealing with science is the scientific method. Can we test whether or not this is man-made with the scientific method? So one thing that we are observing is that it does seem like the world, at least right now, is getting warmer. Temperatures do appear to be trending upward. Also, as people, more people become, as more people use cars and more nations become more industrialized, yes, we are releasing more carbon emissions into the atmosphere. The thing that we have to keep in mind, though, if we're going to deal with this accurately with science, we have to remember that in order to see if there's a relation here, in order to see if there's causality here, we need an independent variable. We need to be able to change one of these two things to see how the other would respond. We would need to be able to curb our carbon emissions and then see if the climate followed that. If we can't do that, this is all just conjecture. I mean, it's just scientific method stuff. And I know there's passionate voices on both sides. Hi, Potter. But in the end, this is what it boils down to. Yeah, sure. So yeah, but it does seem to be trending warmer. Now, I do not, personally, I don't see this as a huge alarming thing. One of the things, because there's no way you can prove that this isn't just a cyclical phase that we're going through. One of the things that I hear a lot is, this is awful because we're getting so much warmer than the Earth has ever been. But that's simply not the case. Have you guys heard of the Vikings? Yeah. So the Vikings, I think I told a dad joke about them a while ago, didn't I? Oh yeah, Scandinavian. So the Vikings were around and they were huge about 1,000 years ago. And they came from Scandinavia and they settled in different locations. They were settling in Scotland here, Iceland, Greenland, the northern part of North America where Canada is there. And I'll tell you, they did not settle on Iceland and Greenland because these were big blocks of ice like they are now. They're not big blocks of ice, but, basically they're super cold and they're too cold to really have an agrarian society. They settled in these locations because they were good for raising livestock, good for farming. There's evidence of them being big farmers in these locations. That's not the sort of thing you can do now. But you could do it 1,000 years ago because the Earth overall was much warmer back then. And so the thing is, one of the big things is people say, well, if our oceans rise, then what's going to happen to these big cities that are on the coastlines? That's just awful. You know, places like New Orleans are going to get, you know, flooded. And I guess the way I don't want this to sound callous, but the way I would respond to that is, you know, if you're going to build a city below sea level right next to the ocean, that's the sort of thing that's going to happen. So you want to make sure that, you know, we got to take everything into account here. And if some places get flooded and people got to go somewhere else, if the earth gets warmer, there's more places further north that will be able to be settled. So I don't really see it as this huge deal. In fact, in the 1970s, everybody was saying that we were headed for another ice age. And everybody was saying how awful that was. And Time magazine had much different covers back then. So it's the sort of thing where, you know, 30, 40 years from now, maybe we're going to be trying to blame ourselves for the next ice age. You really don't know. It could just be cyclical. I'm not saying that global warming is not caused in any way by man-made things, but I do think we're getting ahead of ourselves thinking that this is spelling Armageddon. It really irks me when I see like these shows, and like I'm drawn to like disaster-related shows. If you've ever seen something like Seconds from Disaster, I think I watched every single one of those episodes on YouTube. They're on there for free if you're ever interested. They go through these disasters that are just crazy, and they break down exactly how they occurred. And sometimes I see on programs like that, and they say, and the number one threat to humanity is global warming. The number one threat to humanity is, in my opinion, not global warming. Solar flares would surely be much more dangerous for us, because if it happens tomorrow, it's going to be really a lot of trouble. Yes?
Didn't Al Gore say we should all be dead by now?
Yes. In his documentary, I believe it's called An Inconvenient Truth, they made a lot of claims that by now we would have passed the point of no return, and by now things should be getting just awful. And they haven't. You know, we live on Earth, and the Earth regulates itself, and a few cars driving around I really don't think is going to change that. And I know a lot of people feel passionate both ways, and there's a lot of evidence out there. All I really want to say about that is when you use the scientific method, you have to be humble about what those things are capable of. And we don't have the information, we don't have the independent variable that could tell us whether or not this is actually occurring. And this was just within one of those articles, the scientific evidence showing that our temperatures are going to dip and we're headed for an awful ice age. So yeah, these things come and go. Try not to lose sleep over it. And I think we're just going to close with some neat pictures of the sun. So I'll turn the rest of the lights on. I'll be back on in a second. Sorry. Doesn't that look? I'd love to just sit on that beach right now.
Yeah.
Or that one.
I'll sit on that.
Yeah. So there you go. The sun. Quiz on the sun tomorrow.
Are we gonna watch the video of